This is a bridge converter and I will show you how it works. So we have a voltage coming in and a voltage coming out. We want to calculate the voltage load here based on V in. And they are controlled through 4 different control signals. And this is a bidirectional switch. So when the switch is on, the current can flow through the switch. And when it's off, it could flow through the diode. But for now, you don't need to think about all of these diodes because that is only relevant for when the power flows from the load to V in. So first, we're going to look at when the power flows from V in to V load. So let's start with the switching. So now we're going to look at the switches. So we want to prevent short circuit. So we know that Q1 and Q2 could never be on at the same time because then there will be a short circuit over here. And it's the same for Q3 and Q4. And that leaves us with only 4 combinations. So the first one is when Q1 and Q4 is on. That means that the flow will go from the top here and through this switch and then into the load on the positive side. And out, the flow will go through the switch here and to the negative side on the in, which means that V in should be equal to V load because there's just a wire here, right? So V in is equal to V load. And when Q3 and Q2 is open, it's the opposite. So the flow will go from the positive side on the left side to the minus side. And here we go from the positive side to the minus, right? So that means that V in equals minus V load. And when Q1 and Q3 are both open, both would have a potential of V in, right? Because it goes like this, which means that the V load would be equal to 0. So V load is equal to 0. And it's the same for Q2 and Q4. So it will go here to the positive side and here to the negative side, which means that V load would also be equal to 0 here. Now I just move the V load to the left side on these equations here. So now I want to look at the control signal. So the control signals are only pulses here with a specific width. And I've set them to a duty cycle with 50%. I've also shifted the Q3 and Q1 a little bit. So we also get where this scenario here, these two here. It's the same for Q2 and Q4. So now we want to calculate the V load. And we only use these equations here to find it. So we look at what happens first. So first, V4 here is on and Q2 is on. That corresponds to this scenario here, which means that V load should be equal to 0. Now Q4 drops and Q3 goes up, which means that for this period here, the voltage should correspond to, so it's Q4 and Q2. No, Q3 and Q2, I mean. It's this scenario here, so V load is equal to minus V in. We can just draw it down here, and then for about this length. And now, what happens now is that now Q2 drops here, and Q1 rises. So that means that Q1 and Q3 is on, which means that V load is equal to 0 again. And then Q3 drops and Q4 rises again. So now it's Q1 and Q4, which is on, which means that V load is equal to V in, which is high for a specific amount of time here. And then if you see the pattern here, it will continue like this for the rest of the period, right? Or the voltage should therefore end up looking like this. So the current depends on the load. So what we want to do is to do V load divided by Z load. If the load is resistive, we get a waveform like this, just scaled, because a resistive load is constant. But if the, for example, load is inductive, we will get something else. So for the case where the load is inductive, we know that VL is equal to L multiplied by the change of current, right, over the time. We can just get rid of this here, which means that the IL is equal to 1 over L multiplied by the integral multiplied by the multiplied by the integral of VL over time, right? So what this equation tells us is that we integrate each part of this V load and scale it with 1 over L, okay? So first, V load is 0, which means that if you integrate 0, you get 0, or a constant, but yeah, let's say 0. And if you integrate something negative, you get a negative rate of change. And then you have 0 again. When it's 0 now, it would outcharge itself. So now the V load is at 0 again, so it would be 0 when you integrate as well. So now VL is positive again, so it rises again, like that, right? And then it's constant here, then it falls again. So it continues doing this for the rest of the cycle. So at the end, it would end up looking like this. We don't know where it starts, so this doesn't need to be 0 at the start, and it doesn't need to be 0 at the end. That depends on the system here. So you maybe wonder what happens when the current here is constant, because then the switch here, for example, on this one, the switch Q3 and Q1 is on, which means that these two here are on, but they cannot flow any current here, right? So that means that the current, which initially is negative, right? So it continues, so it flows this way. So it continues flowing this way and goes through Q1, right? And there is a current also going from here and through the diode into the load. So what happens is that there is actually some power flowing from here to here, which means that this line here is actually not flat, is actually rising a little bit, but it's not much because we have such a big L, or it depends on the L. The larger L, the less of a change there will be. And for when the current is positive and flat, it would just be the opposite case. So the current will flow here, right, through the diode here, and then it will come up through the switch here, right? And then the current here will be falling a little bit because it's transferring power. So what we can do with all of these diodes here is that we can use it as a rectifier as well. So if, for example, we say that there's a battery here and we have a motor here, let's say a boat motor. So when we want to brake or accelerate, we apply power here from the battery and onto the motor. But if we want to like brake, but not fast, but slowly, so if you use the motor to generate power, you can rectify this power flowing from the motor into the battery, because your motor needs AC power and the battery needs DC power.